States and in Canada. Good end of the day for those of you who are in Europe. So my name is Pooh. I'm leading the products and partnership team at Klabs, and today I'm going to talk to you about how to future-proof the existing multimode fiber cabling infrastructure in local area networks. Before we start to delve into the topic, just a few words about the organization of this webinar. So I have a few members of the communication team at Klabs who are supporting me during this webinar. There is a chat on the bottom right side of your screen. Don't hesitate to use it if you have an issue with the sound, with the video. You can also use it to ask questions, and they will be moderated by my colleagues, and we will look at your questions at the end of my presentation. So to start, just a few words about Klabs. We are a French company. We are a rather young company, 6 years old, and we are a deep tech company, which core activity is to develop, manufacture, and sell innovative optical components around beam shaping. So at Klabs, we have developed a unique technology for beam shaping called multiplane light conversion. And we are developing products and solutions around this technology and around beam shaping in general for a large area of applications. What do we call exactly beam shaping? Beam shaping is basically using a property of light that is usually not used in communication, especially. Usually we use power, we use wavelength, we use polarization, we use phase in order to improve the process, increase the capacity of a communication. And here at Klabs, what we do is that we control the shape of the light in order to also improve all these processes or these applications. And this has a lot of different area of application. It goes from laser material processing, so laser welding, additive manufacturing, applications like that, to communication between Earth and a satellite, for example. But for today, I'm going to focus on how beam shaping can help for fiber multimode fiber infrastructures in local area networks, and how we can help with old fibers, old infrastructure by using beam shaping. So to start, how do we increase the bandwidth needs? What increases the bandwidth needs in a LAN infrastructure, and how does that affect the LAN infrastructure? Today, in order to have a productive network, a network that is that brings the most to your users, you need a lot of activities, a lot of services, applications that require a lot of bandwidth. To give you a few examples, a good Wi-Fi requires a few gigabits per second already in the backbone of your network. Today, we use everything smart, smart factories, smart buildings, smart cities. All these smart applications, all these IoT applications, they require a lot of bandwidth as well. We also deploy a lot of CCTV. For example, we deploy audio, video streaming across the companies. And these apps, these services are really bandwidth consuming. So most of the equipment that are shipped today for networks are at least at 10 gig per second. And for the backbone of your network, you need at least 10 gig per second in order to have a productive network. However, the infrastructure of your local area network may not support this bandwidth needs. Indeed, a lot of existing infrastructures are based, a lot of existing backbones are based on multimode fibers. Some data show that up to 80% of the fibers in local area networks are multimode. And these multimode fibers are still deployed today in local area networks, but they are not able to offer unlimited capacity. And from our estimation, for example, 35% of the multimode fibers that are deployed in local area networks can only offer up to 1 gigabit per second maximum. And they are not capable of supporting the productivity that is needed in a modern local area network. So the standard solution, the most obvious solution, is to roll out new fibers to replace these multimode fibers. But this is not necessarily the easiest or the cheapest way to do it. So we are going to look into how we can deal with that and why this is a problem. But just to start with, a quick survey to see if you know how the limitation of multimode fibers apply. So according to you, what is the maximum distance that can be achieved at 10 gig over, for example, the oldest generation of multimode fibers, OM1 fiber or 62.5 micron core fibers? So is it 220 meters, 600 meters, 33 meters, or 2 kilometers? Okay, so about half of you have answered the questions, and I see that there's a lot of good answers. So yes, indeed, the answer is 33 meters. This is the standard limitation of OM1 fiber. I see that some of you have also answered 220 meters. We are going to see later that this is also kind of a good answer. So 220 meters or 33 meters for OM1. More generally, for all types of multimode fibers, you can see here the limitation of bit rates that they represent. So for all fibers, obviously, if you are 100 megabit per second, you can achieve very long distances, and this is never a limitation. However, when you move to 1 gig per second, already they are limited below 600 meters, even for the latest generation of multimode fibers. And you may have longer than 600 meters of multimode fiber in your network, especially in a big campus between buildings, for example. And when we move to 10 gig per second, then the oldest generation of multimode fibers, such as OM1 or OM2 fibers, are really, really limited. They are limited below 100 meters, and this is extremely short, actually, for local area networks. So you see that multimode fibers may represent a limitation. Why exactly are they limited? The cause of this limitation is a physical phenomenon called modal dispersion. Modal dispersion is a distortion mechanism that occurs only in multimode fiber, not in single mode fibers. What exactly is this distortion? Well, it's due to the fact that multimode fibers, as the name multimode says, have a lot of different shapes, a lot of different modes that travel inside this fiber. And each one of this shape actually has a different speed, a different propagation speed inside the fiber. So if you look at the signal that is launched into the fiber, it's actually spread across a lot of different shapes, a lot of different modes. And each one of this shape is going to travel at different speeds. And so at the end, the signal is going to get mixed. If we looked more into detail at different examples, if we look at a signal at a 100 megabit per second, for example here, you have a very clean signal at the beginning, of course, when you launch it. And after propagation, even though each mode has a different speed, because we have a very long pulses for 100 megabit per second, at the end you have a signal that is a bit distorted by modal dispersion, but that is still recognizable. And so here you would still have a perfect transmission. However, if we move at 10 gig per second, now the signal, the pulses corresponding to each bit of your signal is much shorter. And so at the end, the distortion due to the different speeds is much larger, and you end up with a signal that doesn't look anything like the signal that you had at the beginning. And so if you try to match them, you see that there are a lot of errors occurring in your transmission, and you are not capable of having a good transmission at 10 gig per second when you have a long multimode fiber. This is the reason why modal dispersion is limiting multimode fibers. Now, how can we overcome this limitation? I talked a little bit about using new fiber, but there are maybe other solutions. So first question for you, do you know or have you used techniques to upgrade the capacity of an existing fiber cabling infrastructure? And if so, which ones have you tried? Obviously rolling out new fiber, but also have you tried parallelization, WDM, advanced modulation formats, or mode conditioning patch codes? Okay, so I see that a lot of different things have been tried. Most of you rolling out new fibers, but also various different techniques. So this is good. It means that you know a lot of different techniques for upgrading an infrastructure. So now let's review all of these different techniques, each one of them, and see which are their pros and their cons. So to start, advanced modulation formats. Here, the idea is to use your existing fiber and to increase the capacity by increasing the spectral efficiency of the fiber. By spectral efficiency, what we mean is that we use different degree of freedom to increase the number of bits that can be transmitted at the same time inside the fiber. So this could be done by modulating the power, for example, with some PAM-X, PAM4, for example, PAM8 modulation. It can be done by modulating also the phase or the polarization, but in that case, you need a coherent detection, a coherent transmission. And these, basically all these are rather expensive to deploy. They need expensive hardware, especially when you use coherent transmission. And most of the time, they are not necessarily compatible with the economical equation of a local area network. So they are indeed a good way to increase the capacity, but not necessarily for LAN, more usually for long-haul networks. Then another way to increase the capacity of multimode fiber is actually to parallelize a lot of multimode fibers and to use a lot of them simultaneously. In that case, we're not really overcoming the limitation by itself, but we're rather bypassing it by using a lot of multimode fibers at the same time and then aggregating the data which is transmitted across different fibers. So there are a lot of there are equipment hardwares that are already designed for this kind of parallelization. You have multi-fiber connectors for the physical interface with the fiber, and you also have transceivers that perform this aggregation between the different fibers, usually QSFP transceivers. So this is something that can be done, but it's mostly used for new projects because you cannot really reuse the existing infrastructure to implement that. It's not necessarily very convenient to do that. Also, the maximum capacity of each fiber remains the same. So you're not really gaining any capacity. You are just aggregating the capacity of different fibers together. So this is not really used for upgrading existing infrastructure. It's more interesting if you're deploying a new one. Another very common technique is wavelength division multiplexing. So in that case, we enable multiple channel over a pair of fiber by using a lot of different wavelengths, a lot of different colors, so each color being a different channel. And in the same way as for the parallelization, you're not really increasing the capacity of the fiber, you're just using more channels inside the same fiber, and you're aggregating it at the end. So it means that, well, you need hardware to do the aggregation. And also you're using, it's a bit more complex to deploy WDM because you need a variety of transceivers, each one for each color. So in terms of maintenance and of supply, it's a bit more complicated. It can be used in local area network, and I think it is used in some local area networks, but it's still limited in terms of use, in terms of deployment, because of this complexity, and also because, once again, you're not really gaining in capacity, so what you're achieving is a bit limited in terms of gain. The most obvious way to deploy fiber, we have already said it, it's to deploy a new fiber. So either a single mode fiber or a later generation of multimode fibers, such as OM4 or OM5. In that case, you are really increasing the capacity of the link by deploying this new fiber. Also, if you're using a single mode fiber, it's really future-proof because the capacity of the single mode fiber is virtually unlimited. However, there are a lot of drawbacks also in the deployment of a new fiber, especially in terms of complexity. So you need to do an audit of the site. So you need to really look into detail into the existing infrastructure. Sometimes the installation may be long and complex to roll out new fiber, especially if you have a big campus and you need to roll out fiber over a long distance. Potentially, there could be civil engineering. There could also be downtime for the enterprise or for the factory where you are deploying the fiber. And when you have all these complex cases, even if you can afford the time it requires, it means that the project becomes very expensive, and you can reach several tens of dollars per meter of fiber if there is this kind of complexity, if there is engineering work, if there is a complex installation to be done. So sometimes deploying a new fiber is just not relevant economically for the customers and for the installers. So sometimes doing this is simply not possible. It's the most future-proof way to improve your network, but it's not necessarily possible in all cases. So if we look at that, there is the last way to do that, and the person who answered 220 meters for the limit of OM1 probably knew about this technique. It's called mode conditioning or offset launching. Here, the idea is that instead of exciting all the modes, all the shapes with different speeds that are in the multimode fiber, you try to only excite a few of them, and so to limit the effect of modal dispersion. This is done by using what is called a mode conditioning patch cord. So this is a patch cord that does an offset launch inside your multimode fiber, and onto that you add the use of a special transceiver called a long-reach multimode transceiver, RRM transceiver, which does some signal processing. So it's some dispersion compensation, which is done electronically. So by using that, you can potentially get up to 10 gig, up to 220 meters over OM1 or OM2 fiber. So this is a small increase in capacity, but it's not very reliable. It's not guaranteed to work on all infrastructure. Basically, if you look at what the manufacturers of this kind of solution tell you, you have to plug it on your network, look if it works, and if it works, great. If it doesn't work, then you still need to deploy a new fiber. So it might be worth it if you have around 200 meters of fiber to try this, if you need this small capacity increase, but there's no guarantee it's going to work, and it's still not the right solution if you have much longer fibers on your network. So if we review all these alternatives to increase the capacity of multimode fiber, we see that there's no really a perfect solution. So either the capacity increase is a bit small, or it's too complex to deploy or too expensive to deploy for a local area network. So the question is, does a perfect solution exist? Well, if we look a little bit into what the RRM solution does, then we see the hint of the fact that, yes, there should be a perfect solution. And the perfect solution is not to reduce the modal dispersion as the mode conditioning patch code is doing, but actually to remove completely the modal dispersion. If we are able to achieve that, then we would have the perfect solution. So the question becomes not does the perfect solution exist, but how do we implement this perfect solution? How do we remove the modal dispersion? Well, the answer is in the physics, in the modes. So how to remove modal dispersion? It's by controlling precisely the modes in the multimode fiber. So it means controlling precisely the shape of the light. As I said before, the modal dispersion is caused by the dispersion between the velocity of the different modes inside the fiber. So if you want to avoid this dispersion, if you control precisely one mode inside the multimode fiber, then you would not have this dispersion. And this is exactly what the technology that Skylabs developed, the multiplane light conversion, can achieve. Multiplane light conversion, I'm not going to go into detail into how it works, but basically what it can achieve is a free-form beam shaping. It comes from quantum optics, so it's a very complex shaping can be achieved. It's completely passive and it's almost lossless. There's no loss in changing the shape of the light. And so by using this technology, you can actually excite only one mode in the multimode fiber instead of exciting all these different modes. And by doing this, you actually achieve what I described as the perfect solution before. So the solution that completely avoids modal dispersion. And if we look into it more in detail in the bandwidth gain that you have with that, this is a drawing in terms of bandwidth against compared to the light launching conditions. This is something that is from IEEE study. Well, what you see is that with offset launching, what you're doing is you're launching on the side of the multimode fiber, so you excite some of the higher order modes, and by doing that, you have a small increase in small gain in the bandwidth. With what we do with multiplane light conversion, we have a perfect center launching, so we are only exciting the center, the fundamental mode of the multimode fiber, and so there is only one mode traveling inside the multimode fiber, which means that you're basically having a single mode transmission inside your multimode fiber. And by doing that, you obtain exactly the capacity of a single mode fiber in your multimode fiber. So you have a perfect, infinite bandwidth gain by doing that. So how can we implement that in reality? How can this be deployed on your network? This is done with our product, which is called Aruna. So Aruna is basically a simple box, a simple component that you put at the end of your fiber, which does exactly that, which does this perfect center launching on your fiber. So it increases the capacity of the multimode fibers. You can get 10 gig in your fiber. You can even get more than that because basically you have a single mode channel over your multimode fiber. It's cost effective because there's no work on the fiber. You're not deploying a new fiber. You're simply installing something at the end of the fiber. So it's in a very contained way. It's simply in the server room of your network. So this is 3 to 10 times less expensive than a fiber rollout. It's completely passive. You don't need any power to operate this system. And it's very easy to deploy. So the installation can be done in half a day, usually about 1 hour for one pair of fiber, basically. So half a day, maybe a few days if you have a very large network, compared to days and days and days of work with a new fiber deployment. And it's also compatible with standard transceivers, standard equipment. So it's very easy to use. The Aruna series, so the Aruna products are actually declined over 2 different versions. One is for standard Ethernet on local area networks. So it's called Aruna Star. In this case, we offer basically a single mode transmission over one multimode fiber. So you can have a module that works for multiple multimode fibers altogether, or just upgrade one pair of fiber at each time. And we also have a version of our product for passive optical LAN architecture. In that case, we replace the splitter in the passive optical LAN architecture, and we can take either multimode fiber in input or multimode fiber in output of the splitter. More precisely, the Aruna Star. So it's really one component to upgrade the network to 10 gig or even more. You can upgrade one pair of fiber, or you can use one component to upgrade up to 12 multimode fiber simultaneously. And it's compatible with wavelength division multiplexing. So you can even use more higher data rate transceivers, for example, 100 gig transceivers over this Aruna Star system. And it's just one unit at the core of the network when you have short links. So it's a very easy to install. The Aruna POL, Aruna POL for passive optical LAN. In this case, so as I mentioned, it's a replacement of the splitter in a passive optical LAN architecture, and it can adapt multimode fibers to single mode fibers inside the splitter. It works with GPON and XGPON, and for this specific product, you can get it from us, but it's also integrated by Tellabs in their FlexSim product line. So this is also something that is compatible with a lot of different manufacturers of passive optical LAN equipment. So where can this be used? Well, it basically can be used basically on any network. As you see, it's very easy to deploy. It's compatible with any kind of network architecture, and it's specifically relevant when you work with large campuses, such as factories, hospitals, universities. These are cases where, well, you have long distances because you have big campuses. You cannot necessarily afford downtime, especially with factories or with hospitals. And so an easy installation, a cost-effective installation is the best you can get for these kind of campuses. To give you a few examples of deployments that have been done with Aruna, I'll give you 3 case studies. The first one is what we have done with the University of Georgia Tech. So they wanted to, they have a very big network with fraternity houses scattered around the campus. And what they wanted to do is to bring 10 gig over all the fraternity houses. And so they had OM1 fibers, which were rather long, between 400 and 1 kilometer long. So they could not use, for example, multi-conditioning patch cord to upgrade these links. They could not afford to use, to deploy a new fiber. It would have been extremely expensive to deploy new fiber across the whole campus. And what they achieved with Aruna was to upgrade. They upgraded 35 links actually with 6 boxes from KLabs, and they got 10 gig over each one of this link. And this project was very easy to deploy for the customer. He did it by himself basically, and it was much less expensive than deploying new fibers across the campus. Another example is a factory in France. So this is a steel industrial site, which has a lot of constraints in terms of safety. And so they could not afford downtime, and they could not afford all the safety measures that would have been needed in order to deploy a new fiber. So it was not even worth getting a quote for deploying new fiber. This was simply not possible in terms of operation for this network. And in that case, we upgraded 8 links between 800 meters and 2.4 kilometers on this site. And this was done with no construction work and no downtime. And today it's running at 10 gig, and they have plans to run it at 100 gig in the future because they are deploying a smart factory program in this factory. A last example with passive optical LAN. This is a case we have done with IBM in France over a governmental building, which is dedicated to green, to sustainable development. So they really wanted a green network, which can be done with passive optical LAN, and they also wanted to not waste their existing fibers, which were OM3 fibers. And so in that case, we enabled the deployment of GPON over the campus without deploying new fibers on this site. And again, it was much more cost effective than using deploying new fiber, and there was no service interruption for the customer. I've shown you a few examples at 10 gig. I said that the product is giving you a single mode capacity. So what about the product beyond 10 gig? Well, it's not deployed yet in our customers' network because they're not using over 10 gig yet. But you see here some tests that have been done by our partners with Aruna in order to test whether it works above 10 gig. And it has been tested at 100 gig with commercial transceivers, 100 gig transceivers, so CWDM4 or LR4 transceivers. And they have also been tested for passive optical LAN with XGPON1 or 10GPON products. And also, even in the future, if you want to look really into the future, the Bell Labs at Nokia have tested it with some non-commercial transceivers and non-commercial equipment, but they have achieved 14.5 terabit per second. So that's 14,000 gigabit per second over 2 kilometers of OM2. So this shows you that it's a really future-proof solution. So to conclude, what message should you take home after this webinar? Well, first, I hope that with this webinar, you have now understood why multimode fibers are limited in capacity. It's because of their modal content. It's because there are multiple spatial modes inside multimode fibers. And there are many techniques to overcome this limitation, but the most future-proof and the easiest one is to tackle this mode problem, this modal dispersion problem. So the most future-proof is probably to deploy a new single-mode fiber. But if you want to do something that is simpler than deploying a new single-mode fiber, then really doing the perfect mode launching condition is the best way to increase the capacity of your network. And thanks to Kylab's beam shaping technology, our product Aruna actually enables this perfect launching condition. So you can get single mode capacity over multi-mode fiber in a very cost-effective way and in a very easy to install way. I've reached the end of my presentation, so thank you for your attention. And now I will answer some of your questions. So, are you shaping lights at existing 850 and 1300 nanometer light weights? Well, the shaping technology itself works at any wavelength. So it's shaping the lights both at 850, at 1310, at 1550 or so, which is standard wavelength for transceivers. However, at 850 nanometer, the transceivers are multi-mode transceivers. So they are not adapted to do a single mode transmission. In that respect, we are shaping the light at 850, but it should not use 850 nanometer transceivers over this upgraded fiber because you want to use single mode transceivers, single mode transmission over this upgraded fiber. WDM is what is used in passive optical networks. Well, indeed, there are multiple wavelengths that are used in PON. Usually there are 2 wavelengths that are used in PON, but because our product is insensitive to the wavelength, we are transparent to the wavelength, and this is why we are actually compatible with PON. You mentioned that your system is passive, no power, right? Yes, that's right. It's completely passive. It's just an optical component. It basically looks like a distribution panel, or you can be put inside a distribution panel. You don't need to plug it on the wall. It's completely passive. Okay, so we've reached the end of this webinar. Oh, sorry, there's actually another question coming. What is the smallest size footprint this technology can be implemented? So it's actually very small. Maybe I can show the photo again. It can be seen here. So it's the small module that is here inside a patch panel. So as you can see, it's really slightly bigger than your patch cord, but it's basically fitted inside your patch cord. Maybe I can find a better photo. Well, the quality is not really there, but you can see here. So these two are not at the same size. This is actually very small. You can see the connector here. So this is the size of the module for one pair of fiber. When you want to upgrade multiple fiber, we provide it in the form of a rack, but it's actually rather empty in it. It's just for convenience that it's provided in this size. Okay, so I think we've answered all the questions. Thank you for attending this webinar. If you have other questions afterwards, you can reach me at this email address. Oh, one more question. Well,
I'm just waiting.
Okay, I will wait for the last question. What is the largest density of this as well? So the largest, this is a good question. As you've seen, the small is rather, the size is very small and I think in the best case, we have tried in a 1 euro rack, we had 12 by 4, so that's 48 fibers upgraded simultaneously in a 1 euro rack. This is the best, I think, that we have achieved with our system. In the standard packaging, it's 12 fibers that are upgraded in a 1 euro rack. Okay, so I think this is all. Thanks for attending. If you have more questions, feel free to contact me by email. And we thank you for attending this webinar. Bye-bye.